Well, I knew I was going to be asked that again. I was just giving people who had arrived early, the chance to ask a question while we were all sitting here.
When we put answers to answer boxes, so we don't need to put units, right? Only numbers.
Yes, that's right. You need to follow the units that I ask you. So a question that will ask for a number, so let's say it's the sailboat that's drifting, and it's got the wind and it's got the drift of the current, and you have to add them together. You could give me a lot of those answers in the text. They actually give them to you in kilometers, even though all the calculations you do are in meters. So you could do it either way. I will say, here's the problem. Give me the answer in meters.
If we forget to convert it to meter, like if we forget, like let's say you ask for kilometers,
Yeah.
and we forget to like make it in kilometers, do we get like 0 for that question, or will you give us like part marks?
Well, the thing with those kinds of questions, where there's just a number there, with E-class, these aren't ones like I can have a question that we mark for you, and there will be questions in the second midterm where we will actually mark it. But this one is marked by E-class, so E-class will look at it and go, if you give it, 1.5 kilometers instead of 1,500 meters, E-class will not think that it's correct, because 1.5 and 1,500 are not close. It does allow me to create questions where you could give me any of those: 1.5 meters, 1.5 kilometers, 1,500 meters. But the list of answers that I have to give is quite substantial, because I have to figure out all the ways that somebody might list their, capital K, small k, maybe a space, maybe not a space. And I would, so it's, and what ends up happening is if you don't get it quite right, you will, I had this experience last winter, which of course was the first time I had been doing the quizzes on E-class with them, using these ones. And you guys kept getting, the people writing it would get something that it wasn't, complete, even though it was. So that was distracting. So long and short of it was, if you give it to me in kilometers and I ask for it in meters, then no, you won't get it right, because it won't be marked by E-class as correct.
Like don't you like usually go over after though, just like make sure that E-class didn't make any mistakes?
I will do yes, in broad terms, yes. So what I do afterwards for all tests that I do with E-class is that I will look at every question to see, and I will do a sample. I am not going to mark every question by every student to recheck. What I will do is I will go and take a sample of questions, and I always do this. I always take a sample and I just confirm that they were marked correctly. But the thing is, if you give me 1.5 and I've asked for it in meters, I'm going to mark it wrong too. Right?
I mean, like, if if I was grading, I'd give like part marks. It shows that you understand the material, you just make a mistake. And in a situation of high stress, which is an exam, people are stressed, people make mistakes, which is totally normal to me, but I don't know.
Totally. Trust me when I say, in this course, I am well known for giving many part marks, but I'm also known for taking off part marks for not putting units or something like that. So here's the balance. The answer is given. I don't see any of your work, right? See, that's the other thing. I don't see any work. As much as I would love to see work. And that's why, we are not, I never do this. Even if you were doing this on paper and pencil, it would not be 100% multiple choice, because I like to have you work through a few problems, and show me that you understand it. You just putting down 1.5 instead of 1500 doesn't, I have no way of knowing what your thought process is for the 1.5 versus the 1500. You might have thought that it was 1500 meters. I don't know how you got that value. So if I'm asking you and I clearly say I want it in meters, and you give me 1.5, then it makes me think, well, you didn't really understand what was going on. So how can I give you part marks for that?
Okay.
I mean, that's for a question that's worth 1 mark, right? So the part of the reason I do the matching is so that I can give you part marks, so that I can maybe have you work through a problem and you'd be calculating different things and they would match some of the things that would be matching. That's my one way of giving you guys part marks for some of these questions. And that's why I do it, do some of the matching ones.
Mm-hmm. Thank you.
Okay. So yeah, again, I love to give, if somebody's doing it and they just plug in the numbers wrong, I will always give part marks, but it's just, I can't follow that thought process here. If it was if I had set it up as a multiple choice, you would have got it wrong, right? If I had done the same thing in a problem and then given you 3 answers and you chose the wrong answer, you would have got it wrong the same way. So it's an analogous. For those who have just come on, we are now officially past the start time. It'll be a 45-minute midterm. There will be 3 types of questions. There will be multiple choice, short answer, where you just plug in basically a number or a word into a box. And there will be some matching questions. So you've got something on this side and you match them with other things. And you will be allowed to go back and forth.
How many questions will there be?
Well, it's not, it'll be out of 40 marks, but it's not 40 questions. Because some of the questions are worth more than 1 mark. So I don't have that number in front of me right now, but be out of 40.
So in terms of like the values of the number, are you going to tell us what to round it to? Because depending on how we round it, the answer differs. So will you?
Well, that one I always do check. First of all, there will be a it will be, I will tell you, there is some wiggle room there. And again, yes, I do check over them, but not enough that I would give somebody who said 1.5 instead of 1500 the full marks. I would go through and see, when I look at ones where people have actually put units in, I just confirm that they get the marks, because I do quickly scroll through there. And I make sure that the window for round off is appropriate, just to make sure that people, would get what they were getting with some round off. So yes.
Okay, thank you.
Perla, I think you.
Hi, morning, Professor. Can I ask a textbook question?
Sure.
Is it possible to do chapter 10, additional question 7?
Chapter 10, question 7. The soccer ball at
Yeah.
5 degrees? Sure.
Thank you.
Okay, so let me just share the whiteboard now that I can get a whiteboard on here. Okay. Hope everything, so now you aren't going to see me for a bit because it's just easier for me to draw on this flat. So we are talking chapter 10, additional problem 7. A soccer ball is kicked from the playing field at 45-degree angle. If it is in the air for 3 seconds, what is the maximum height achieved? So we have our soccer ball. It's going to go off at 45 degrees. And it is in the air, and then it's going to come around and it's going to land, and the time in air equals, I mean, that's obviously the horizontal distance, but the time in air is 3 seconds. And what they want to know is the vertical height. Okay, so we know the time to apex. Well, first of all, that's the information we've been given, and we know what we want. We also know that it's going to take off and land at the same height. So the projection height equals 0, which is important to know. Why do I know that? Because if we're on a playing field, typically if you hit on one end of a playing field and it lands somewhere else on the playing field, hopefully the playing field is level. And so they'll be at the same height. It's not kicking up a hill. Playing fields on a hill usually don't work very well. So level, and that means that the time to apex is going to equal half the time in the air, and that's only because because it's level playing field. So that's going to equal 1.5 seconds. Now, the part that we are going, if we go back to our good old equations on page 323, and we're talking for a vertical component of a projectile motion with V2 equals 0, which is what this is. So it starts off with a V1. That would be the vertical component of the at the start. And then it has a vertical component velocity of 0 at the top here, which is, at the apex. That's what defines the apex. It changes direction, and so the velocity passes through, the vertical velocity passes through 0. It stops going up and it starts to go down. And we want to know the distance. So we know the time. We can figure out V1, right? If you look at 1A, we can do this in multiple ways, but let's just start with 1A. So the where if we rearrange that equation so that V1 equals 9.81 times T, and this is the T to the apex. And all I'm doing is rearranging that equation. By bringing V1 over to the other side, it becomes negative, and that accounts for the fact that there's a negative in front of 9.81. So that's going to equal 9.81 times 1.5. This is in meters per second squared. This is in seconds, so that'll cancel and you'll be left with meters per second. So can somebody tell me what that is?
14.7.
Meters per second. So we know the velocity. We can then put that into 2A, and that's going to be D equals V1 squared over 2A, which is going to equal 14.7 squared over 2 times 9.81 meters per second squared. And this is going to be meters squared per second squared. Those will cancel. That'll cancel and we'll be left with meters. So 14.7 squared divided by 2 divided by 9.81.
I think it's 11 meters.
Does everybody agree?
Yeah.
Okay, so mathematically that actually does, I mean, that's the answer, but are there other ways to do that? Yes, you could also use equation 2V, which is D equals 1/2 AT, A times T squared, which is 1/2 9.81 times 1.5 squared. Do you come up with the same answer?
Yes.
Good. Both of those work. This one's, of course, direct, but it does work.
Professor, so how come you didn't consider the 45 degrees?
Okay, why didn't I use the 45? I mean, 45 degrees is a red herring.
Oh, that's because that's what's confusing me.
It's just because information is given to you does not mean that you need to use it. So the 45 degrees really just allows you to break up the vertical velocity and the horizontal velocity, right? It allows you to take whatever that initial projection magnitude of your projection velocity and split it into two components, one that's a horizontal velocity and one that's a vertical velocity. If it's 45 degrees, I'm going to tell you this right now, that the vertical velocity and the horizontal velocity are going to be the same. So they're both going to be 14.7 meters per second. So this is one of those situations where you can take even though it doesn't give you the answers to it, but if you wanted to, and just to practice, you could then go on and say, because I've been given that it's 45 degrees, I can figure out what this initial velocity is. Not that I'm asked it, but I could. I could also figure out what this horizontal velocity is. Not that I'm asked it, but I could. And I could also figure out how far it's going to travel in that distance. If I also wanted to know how far it traveled, I could do that because I've got that 45 degrees. Does that make sense?
Yeah, so you didn't have to use it for the height because I guess the vertical velocity is like, I don't know how to say it. I don't want to say it doesn't matter, but I guess it doesn't.
The reason you don't need it for the first to do it is because you can solve this without knowing ahead of time what this vertical velocity is. See, I can calculate it. So this is the vertical velocity at time 1 is right there. That's the 14.7 meters per second. So from the apex time, or the time to apex, I can actually calculate what this is. I don't need to know what this guy is and this angle is. You know, in a lot of the questions, you know, the ball is taking off at 20 meters per second at an angle of 30 degrees. And then you use that information to calculate this vertical velocity. And then you calculate the time in the air and all those things. But this time you have the time in the air. So you don't need to know that vertical velocity because there are ways to calculate the vertical velocity knowing the time in the air. And there's ways, and therefore you can calculate your height, or you can directly go knowing that time to the apex. It's actually not time to air, time to apex. Knowing this time to apex, you can calculate it directly without even having the velocity. That's why there's so many variations. They're just rearranging the equations in different ways so that you can, given whatever information you have, you can plug it in to get what you need. But because you have that time to apex, you don't need to know the vertical component of the velocity. You can calculate it.
Okay, yeah, that makes sense. Thank you.
Okay. Let's.
Sorry, I have another question.
On this one?
Yes.
Okay.
So for the second way of doing it, isn't the formula for when the V1 is 0?
Yes, but you know what? 2V actually works for both. They shouldn't have, they should have actually put it into both. 2V is actually valid for both. It's as long as you know the time from either the start to the apex,
Yes.
or the time from the apex to the end, you can calculate the distance directly from that, from it. So that's why 2V actually works, could also work down below in the third group, because there is no velocity there, right?
Yeah.
You just need to know the time from to the apex or the time from the apex, depending, again, if you're measuring the distance from the apex to the ground or from the start to the apex. Okay, let's go there. And I think, Danny, you were next.
Hi, Professor. I had a question with regards to the formulas, the one on page 323, the ones we keep referring to.
Yep.
So my question is with regards to time. I just wanted to confirm, only for formula 1A and 2A, so the last two, T is time to the apex, not time air, correct?
So yes, you're right. It's absolutely time to the apex. And I corrected myself up there when I said that by accident. But yes, the time, all the 1V, 2V, and 1A, sorry, 1A is time to the apex. 2V is either time to the apex or time from the apex. And 1V is time from the apex. I mean, they're the exact same thing. It's just one has the V2 as opposed to the V1.
Okay. And so that's for T. And as for D, the only one that's the horizontal component is that 2H, correct?
That is the only one that's going to give you the horizontal distance, yes.
All the other will be vertical distance?
Yep.
Okay, great. Thank you.
You're welcome. Okay. So that was your question, Danny? That was the only those were all of them. Julia.
Hi. Could you do chapter 10 intro problem question 10?
Chapter 10 intro.
I'm just confused on which formula to use.
Okay. The trampoline person. Okay. Go to share screen. So the trampoline springs vertically upward with an initial speed of 9.2. So chapter 10. Intro 10. We have basically a person going up. They're going straight up, right? So this is a case where the person is the projectile. They're going straight up, so the vertical component of their projectile velocity is the same as their projectile velocity because everything's vertical. There is no horizontal, which is what you want. If you think about it, if you're going up and down on a trampoline, you want to keep hitting as close to that center spot as possible. You don't want to be traveling, so you want to go straight up as much as possible. It also means that if you're going straight up, think about it. If you're going straight up, that's going to be the case where you're going to get the highest that you can. If you think, if you go back to what angle gives you the farthest horizontal distance and which angle gives you the highest point, well, the one that gives you the highest is always going to be straight up. So for a trampoline, somebody on a trampoline, you want to go straight up because that gives you the most time in the air. It gives you the highest height. And therefore, if you're trying to, if you've watched trampoline at all, you know, the higher you are, the more you're going to get done, more flips and twists and things you're going to be able to accomplish before you land. So, they're going up at 9.2 meters per second, and we want to know what the, so that's V1, well, V vertical 1, which is the only thing it is, equals 9.2 meters per second squared, and they want to know what is your vertical height. So we know what we're looking for. We know what we have. If we come back to, again, our nice, if we look at the equations that we are given, and we look at equation 2a, which is 0 equals v1 squared plus 2ad. And if you're wondering why I use that one, the only difference between what you see in the 1, 2, 3 V's and the 1, 2 A's are that in one case we're using V2 because we're looking at the landing velocity, and because of that we don't have to worry about the negative well, and which means the velocity will be in the opposite direction, so it will be in the same direction as acceleration, which is negative, where it's the opposite for V1. And if we rearrange this, we're going to get V1 squared equals 2AD, and or V1 squared equals negative 2AD, which is equal to negative 2 times minus 9 point. I didn't actually show this out last time, just so you can see why the negatives drop out. Times D. And see, because it's a negative times a negative, this will now become positive, positive. And V1 is 9.2 meters per second, and that's all squared. So if we solve for D, D is going to equal 9.2 meters per second all squared, divided by 2, divided by 9.81. And this will be second squared, so that it cancel. It will lose one of the meters, and we're just left with meters. So if somebody can plug that through.
4.31 meters.
Excellent. All good? Any questions on that one?
No, thank you.
You're welcome. Okay. Kyla.
I was wondering if you can do chapter 11, additional problem 7.
The majorette. Absolutely, no problem. So let's go into share again. Okay, and I have done this before, but it's one that bears repeating. So this is chapter 11. Additional problem 7. And we have a majorette in the Rose Bowl parade tosses a baton into the air with an initial angular velocity of 2.5 revolutions per second. If the baton undergoes a constant acceleration while airborne of -2 revolutions per second squared, and its angular velocity is 0.8 revolutions per second when the majorette catches it, how many revolutions does it make in the air? There's a very simple way of doing this, and that is using those same equations that we see on page 323. Those are the linear versions of them. But if you look at 1, 2, and 3, they're called the equations of constant acceleration. That means so A equals V2 minus V1 over T, right? That's you have a constant acceleration. It's not changing, but during the time frame that you're looking at, you have this constant acceleration. Those same equations work for angular acceleration. So, an angular acceleration is going to equal And so any one of these equations we could do that in. We've got something spinning. And it is spinning at 2.5 revolutions per second for at time 1. Time 2 is equal to 0.8 revolutions per second. The angular velocity equals negative 0.2 revolutions per second squared. And it wants to, the answer wants to know is basically this. And they want it in units of revolutions. So we could from this figure out the time in the air, because this is when they release it, this is when they catch it, and in between would be the time in the air. So let's just do it that way. Time in the air, or the time, well, it's the time in the air, is going to equal 0.8 revolutions per second minus 2.5 revolutions per second over negative 0.2 revolutions per second squared. What's that?
It's 8.5 seconds.
8.5 seconds, perfect.
Yes.
Perfect. So everybody sees that. And the so we have that time in air, and we want to know how many revolutions they were doing. Well, what's their average velocity during that time? The actual average velocity, because it's a constant acceleration, so the average velocity would reflect what it was doing over that time period. So the average velocity is this is a different way than I did it before. I'm just trying to show you that there's multiple ways of doing this, and then I will show you the easier way of doing it, because you can do it in one shot. So that's 3.3 revolutions per second over 2,
1.65.
65, yeah. Revolutions per second. So look at that, and theta equals your angular velocity times time, right? Because angular velocity equals theta over time. So I'm just rearranging that equation. So 8.5 seconds times 1.65 revolutions per second. And that equals what?
14 revolutions.
And that's where you get your 14 revolutions. So those are using the equations that you know, but if, as I said, if you look back in chapter 10, you can use any one of these equations, 1, 2, 3, and just plug in an angular velocity anytime it says v, and the angular acceleration anytime it says a, and d, the theta anytime you use theta. So you are given V2, V1, A, and you just need to find you need to find theta, which it would be the D. So if you look at equation 3, you've got W2, and I'm just putting the angular versions in here as opposed to the linear versions. This equation is the same as equation 3, only with angular measures there. So if we solve for theta, it would be 0.8 squared minus 2.5 squared divided by, sorry that this is getting a little messy in here, 2 times negative 0.2. And these are going to be revolutions squared per second squared, and this is going to be revolutions per second squared, and you're going to be left with revolutions. And I think if you do this, 0.8 squared minus 2.5 squared divided by 2 divided by 0.2, or negative 0.2, you'll also get 14. So you can do it all in one step by using equation 3, but just putting the angular versions in, or you can do it in 2 steps by figuring out the time in the air, and then given the average velocity, you can calculate the distance. Any questions? Either one works. That solve everything there? Okay, I did have question 11, or sorry, chapter 11, intro 2 was asked on the chat. Um, 11 intro 2. Oh, the clock one. Identify the angular displacement, the angular velocity, and the angular acceleration of the number, of the second hand on a clock over the time interval in which it moves from the number 12 to the number 6. Okay. So we have a number hand or a second hand, which is traveling around, and it goes from there from 12 to, so this is 12, and this to the point over here where it is going to 6. So this is a second hand, and a second hand goes all the way around a clock in 1 second. So if it's going from here to here, the time is half a second. And the angle from here to here, I hope you can see, is 180 degrees. The fact that it's negative has to do with the fact that we often think of counterclockwise as positive as a default. In some ways, and you'll see that I do this when we get to when I get to the point where we are putting reference frames in, and when we get to the kinetics of it, a lot of it is what you define as positive or negative. since in the text they kind of say, you know, we're going to call counterclockwise positive in most cases, and that's fine. That means that since this is clockwise, we would consider it a negative direction if we consider counterclockwise positive, but you just have to define it. If you told me that you think clockwise is positive, then as long as you explicitly said that, so I know what a negative sign or a positive sign means, then it's fine. Since this textbook has said that they use counterclockwise as negative, which is very common in the biomechanics world. That's why you get a negative 180 degrees. And you can see the angle between here. So this angle right here is going to be 180 degrees. Since it's going clockwise, that's why they got a negative 180 degrees. Of course, 180 degrees is pi radians. It's the same thing. So 180 degrees equals pi radians, so both negative. The angular velocity equals second hand. Change in angle over change in time, which should be 180 degrees negative. It does ask for the second hand, yeah.
Excuse me, I believe time is 30 seconds.
Oh, right. Okay, goes through the minutes. You're right. I was talking a fast one. I knew I was doing something wrong. Thank you. See, it's easy to make mistakes. It's been too long since we've all used analog watches. So 30 seconds, which definitely makes much more sense. So that's degrees, this is seconds, and that's where you get your 6 degrees per second. And or your pi over 30 radians per second, and your acceleration is 0 because it's not speeding up or slowing down. It's a constant angular velocity. Okay, sorry about that. Any questions on that? Again, some things that we don't use that much anymore. Aaliyah.
Hi, Dr. Moore. I just wanted to ask a few questions. So my first one is about the test. So I came a little late, but I just want to confirm that it's 40 marks in 45 minutes.
Mm-hmm. That's what it is.
Okay. And then for the short answer questions, are we just putting in like the number into a box?
Either a number or a word, yes.
Okay. And then if we're putting a number, do we have to include units as well?
No. In fact,
Okay.
what I'm going to do in order to is I've decided to go without units this time. Again, if you did it on paper and pencil, you would have to include units. Have to. But there are things that, but for this kind of question quiz, just put in the number. I will tell you what units to have it in.
Okay, makes sense. Thank you. My second question, I just wanted to ask about like relative versus absolute angles with regards to the hip joint. So I know that we measure it in relation to the trunk, which would make it a relative angle, right?
Mm-hmm.
But then if the trunk, like, I know that you can measure it technically, like the trunk is upright, so it's at a vertical axis. Wouldn't that also classify it as an absolute angle, or no, just relative?
That's not a hip angle. Hip angle is the angle between the thigh and the trunk. So let's say I'm standing upright. And let's say I class, in between 180 degrees there as 0. If I'm standing upright, I think you could see that hip angle would be 0 degrees. Does that make sense?
Yep, that makes sense.
So if I was lying flat on my back with my legs straight out, my hip angle would also be 0 degrees. Right? Nothing
Right.
relative, nothing absolute about that at all. I mean, clearly my trunk in one case is purely vertical. In the second case, my trunk is purely horizontal. Hip angle is the angle, the joint angle is the angle between two body segments, and it's relative, and you could be in any posture. As I said, you could be like this, you could be like this, and you could be some funky board or something and still be still have a hip angle of 0. The angle of your trunk, the angle of your trunk there's a very good question. I believe it starts at 9:30. I will make sure that I see that there is a question about when the midterm starts at. Midterm starts at 9:30. So anyway, back to absolute. The trunk angle, if you are upright, the trunk angle is vertical, and that is an absolute angle of the trunk with respect to vertical. I could also say that it has a degree of 90 degrees if I was lying flat, right? Because the trunk is now 90 degrees to vertical. So that's the absolute value of the trunk. And when we talk absolute values, we are basically taking a body segment and measuring that body segment with respect to either the horizontal or the vertical. We are not, it's not relative because it's a segment. I could also take the thigh and measure it vertical to or horizontal, which would be the absolute value of the thigh. But the hip angle is the angle between the thigh and the trunk, and it's relative, and it can be the same whether I'm lying flat or standing straight up.
Okay, that makes much more sense. Yeah, thank you.
No problem.
I just had actually one more question, if that's okay, just a textbook question.
Which one? Quick.
Chapter 10, additional problem 8.
10.8. The ball kicked for maximum height. Yeah, we have done it before, but I will do it quickly. So we have a ball. So chapter 10, question 8. The ball's kicked a horizontal distance. It's a projection angle. Yes. We are assuming that it's going to land and take off at the same height, so that the projection height is 0. We know that the distance is D horizontal equals 45.8 meters. And the vertical equals 24.2 meters. And the time in the air is 4.4 seconds. And the time to the apex is then going to equal 2.2, sorry, yes, seconds. So the key here is that when we have a takeoff velocity, so that's our actual velocity at takeoff, and then we have a projection angle, which is always the angle to the horizontal. And when we split our velocity into its two components, the horizontal component and the vertical component, they're dependent on this angle. And so if that angle is less than 45, which is bigger, horizontal or vertical? I'm asking, somebody can just unmute and answer.
Horizontal.
Exactly, VH is bigger. If it's equal to 45, then what's bigger, horizontal or vertical?
They're equal.
Exactly. And of course, if it's bigger than 45, which is bigger?
Vertical.
So as long as we can find our horizontal and vertical velocities, we can compare them in this manner in order to figure out which of these three cases we have. The horizontal velocity is easy. We know they travel 45.8 meters, and they do it in I apologize there, rushing, in 4.4 seconds. It's going to be, what is that, 10 point something? 45?
10.29.
It's 10.41 meters per second.
Whichever one it is. And then for vertical, we come back to our lovely equations on page 323. And we know the time to the apex. We know the, we know the time to the apex. So V1 equals 9.81 times 2.2. Which almost probably approximately 20 meters per second, 20 point something.
It's 21.58.
So 21 versus 10, I think you can see that this is the bigger one, which means we're in this situation, which means it's greater than 45. Any questions on that, anybody? Okay. I have a one that was put into the chat. I do plan to send you out a notice on the midterm. I'm sorry, things got thrown off schedule yesterday because when I went to put them in, as most of you probably figured out, that E-class was down. And then I didn't get back to it. I apologize. I will send it out after this. So the chapter 10 introductory 10, we did that one. Brenda, what would you like?
Can we do question 5, chapter 3, additional problems?
Yep, that was exactly where I was going, but while I was looking for it, so that was in there. Chapter 5, chapter 3, excuse me, number 5. The
additional problems.
Yeah, so the trig solution to a resultant of the following coplanar forces.
Yes.
Okay. There we go. So this is a really good one for showing why I never use Coase law, because you're adding 3 vectors together, which means you don't have a triangle. So as soon as you're adding more than 2 vectors, you're not going to even have a triangle. So you have to divide each of your vectors into a some sort of plane. Typically, what we you know, what plane you're doing depends on just what you're talking about. That plane could be horizontal and vertical. It could be, you know, classic X, Y. It could be north, south, west, east. It could be 0, 180, 90, 270. In all of these cases, what you've got is a nice little 90-degree angle in each situation. And you want to, and if you take whatever vector you have and split it into its 2 components, so in that case, this would be one, that would be the other. Then if you do that with all of your vectors, you can add up all of the ones that are on your, in this case, 0, 180 line, and all of the ones that are in your 90, 270 line, and just add them all up so that you end up with 2 vectors, one that's all in the 90, 270, and one that's all in the 0, 180. And that's what happens here. We can draw it out to begin with, just so you get a sense. So we're going 90 degrees, so up here. $60 N, 90 degrees. And then 120, which would be 90 plus another 30, right? So that we take 90 plus another 30 and go about 80 newtons. That's roughly to scale. And I mean, roughly, you can put this to scale very easily. And then at 270, you have 100 newtons. Something like that, straight down. And your resultant starts at the bottom there goes to that one there, and that's your resultant. So what you end up having to do is take each one of those vectors, and you've got one that's this one right here, which is 90 degrees. So it's going up here, and all of it, 60 newtons at 90 degrees. And it's all in the 90 to 70, so that's okay. The 100 newtons is down that way, and it's all in the 90 to 70, except that it's down. So you're going to end up with 40 newtons down, right? 60 minus 100 means you're going to have 40 newtons down. But that leaves you with this guy right here. And you have to take it, and remember it's 30 degrees to that vertical, which would mean it would be 60 degrees to here. And we would have opposite would be 60 times sine 30, which equals I'm sorry, that's 80. Maybe that's why nobody's saying anything. There you go. 80 times sine 30, which is equal to
40 newtons.
And 80 times cos 30. Again, I can't pick up a calculator at this point on my machine.
69.3.
Pardon?
69.3 newtons.
69.3 newtons. Great. Okay, does that make sense? This is 30 degrees. If 30 degrees, then my thing on my 90 to 70 line should be bigger than this one, and it is. So it's going to be 40 newtons, and then we're going to go back up again. 69.3, which means I'm going to have in this direction 69 29.3 newtons. And the only thing in the other direction, 90 degrees to it, is going to be 40 newtons. So now I can figure out this resultant, and this resultant is going to be 40 squared, 29.3 squared, take the whole square root of it, and hopefully that's going to be 49.57, but somebody can.
Yeah, that's correct. 49.
Yeah, it's correct.
There we go. Newtons. So that's the magnitude of it. It doesn't ask for it, but if you wanted to find the solution for the angle, you could find this angle right here, which you would then add to 90 to get your whole angle. And it's going, the tan of theta is going to be 40 divided by 29.3. So whatever theta is, inverse tan of that, you add that to 90, and that will be the angle from 0 of the resultant. Any questions on that? Okay. So that's done. So that was your question, Brenda, right?
Yes, thank you.
You're welcome. Oriana.
Good morning, Professor. Can you hear me?
Yeah, I can.
Okay, perfect. Okay, so I had a question about chapter 10, additional problem number 9. I'm really confused about what to do for the V1. Because
chapter 10,
additional,
9?
yeah.
A9.
Was when I read the question, like I think V1 is 10 meters per second.
Sorry. I should just have these all marked. Chapter 10, number 9, which is the badminton shuttlecock.
Yes.
Okay. I see a few things, questions in the chat. When I do something and I ask whether you have problems, if you could please unmute and just ask it, because I can't see the chat when I'm sharing. Yeah. So if you have a question about what the question I'm doing, please unmute and chat, because I can't see the chat until after, and then it's kind of too late because it's not there for me to show you. If you drew the angle, the triangle in the other way, and you got the angle between the 180 and the resultant, which is what I think somebody's asking me, which is fine, and that theta, you would subtract that angle from 180 to get your number of degrees, because remember, you start at 0 is kind of your positive x-axis and you keep going around. So if you want to know what degrees it is from 0, you'd be subtracting that angle from 180. Okay, so chapter 10, additional problem 9. Whoops. And we have again, we have our shuttlecock. We can play badminton shuttle, that shape. Struck by a thing, and it takes off at 10 meters per second at an angle of 35 degrees. And then it comes and lands.
Professor, there's some noise from your mic. I don't know what it is. Better.
Better? Oh, okay. I don't know what the difference is, but let's see if it needs to have my keyboard on. Is that better?
Yep, a lot better.
Okay. So lands. Key thing here, it lands at the same height. We know that. We want to know how high it's going to go above from where it was actually hit. That vertical velocity. and we want to know its distance horizontally. Again, landing, the opponent's racket is at the same height as the first person's racket. So we have we know that the time in the air is going to be twice the time to the apex. So first thing we need to do in this type of question is always to split our vertical velocity, or our velocity. To a horizontal velocity and a vertical velocity, or it can be also thought of, you'll also see me draw it, EV, VH, because basically I'm saying these two components, if I added them together like I did there, would equal the original one. So the (10 meters per second) times, it would be considered the opposite, so that's sine 35. So 10 times sine 35.
5.73.
And V horizontal equals 10 meters per second times cos, because that's adjacent. And in the case of projectile motion, if you're given the angle or angle of projection, you're always going to be using cos for the horizontal, because it is adjacent. The angle of projection is with respect to the horizontal. So 10 times cos 35.
8.19 meters per second.
Okay, so this is the point where we stop and we think, okay, it's less than 45 degrees. That means that horizontal is going to be bigger than my vertical. And yes, that is the case. So I've chosen my sines and coses correctly. Really easy to make the mistakes. You've probably even seen me make the mistake, but that's why I always stop and think about what I expect at this point. We know the velocity. We need to know the time. In order to get how far it goes, we need the time in the air. So we need to find the time to the apex. Is going to equal the vertical velocity divided by the acceleration, which is 5.73 meters per second divided by 9.81 meters per second squared. Those will cancel, that'll cancel, and the seconds will come up. So I will have time, which is equal to
0.58 seconds.
0.58 seconds, which means the time in the air is going to equal
1.16.
1.16 seconds. Everybody sees that it's twice that. And the reason we can go with that, because it's a symmetrical movement, projectile motion. And as long as the takeoff height and landing height are the same, then the time in the air will be 2 times the time to the apex. And so the D horizontal is pretty easy at this point in time, because it's just, we just use good old equation 2H that is equal to the horizontal velocity times the time in the air, which is 8.19 meters per second times 1.16 seconds, which is
9.50 meters.
and the vertical so we're going to use, basically, there's a number of equations we can use here. We'll use equation 2a, which is and this will be meters squared, seconds squared. This will be meters per second squared. Those will cancel, that'll cancel, and we'll be left with meters. Again, I do that just to make sure that I've rearranged.
1.68 meters.
Perfect. Okay. Any questions on anything in there?
Yeah, I had a quick question, Professor.
Yep.
Okay, so what all I'm confused about is that in the equation, it's like for the last part that you did, in the textbook, it's V1. So V1 is always the vertical velocity?
V1 is always the vertical velocity at start. So these equations are generic equations that you can use for projectile, but the V1 and V2 are, let me step back again. The horizontal velocity is constant, never changes. So the horizontal velocity at time 1 equals the horizontal velocity at time 2 equals the horizontal velocity at time 3. Throughout the whole thing, your horizontal velocity, assuming that there's negligible air resistance, the horizontal velocity is constant because the acceleration equals 0. And so there is no need for a 1 and a 2. The 1 and 2 that are used for the vertical ones are basically the vertical velocity at time 1 and the vertical velocity at time 2. And in this, if you have the velocity at the beginning, which is this guy right here. So this is really what I would call the vertical velocity at time 1. The vertical velocity at time 2 is when it reaches the apex, and all the way up to the apex, the vertical velocity drops and drops and drops and drops and drops until it hits 0 at the apex. So the vertical velocity at time 2 equals 0 meters per second. And that's what the 1 and 2s is. And that's the only difference between 1, 2, and 3V and 1 and 2A are whether you have the apex at the start, which is the first 3, or the apex at the end.
Okay, that makes much more sense. Thank you.
No problem. Any other questions on that?
Dr. Moore,
Yeah.
sorry.
There you go.
For the same question, in the textbook, the answer for the horizontal distance, they say it's 9.58. Do you think that's a mistake?
So I haven't plugged the numbers in, and maybe somebody can plug the numbers in with without any round off. And just make sure you get the same number. If they don't, like, so at the 0.58 versus 0.50, it's one of two things. It is an error. What we've done here is correct. Okay.
Okay.
I can't tell you that it is or isn't a round off error.
The value is correct. We just forgot to carry the values for the time. So if you use 1.17 seconds, then you would get 9.58 meters.
Yeah.
Okay,
There you go.
thanks.
I thought it was a round off error. So that exactly is what it is. It's a round off error.
Thank you.
Professor,
Oh my gosh.
sorry.
It's okay.
So for equations 1, 2, and 3, V2 is always going to be the apex, or is it just for this question? I'm just trying to make sense of the variables for all of these equations, because my biggest struggle is figuring out which variables represent what in the context of the different questions.
And I get that. And once you've done lots of them, which I've done these multiple times, you do tend to shortcut a bit. But so 1, 2, and 3, 1, 2, and 3 without an H or a V or an A beside it are generic equations for anything with a constant acceleration. And that it doesn't even just have to be a, projectile motion, any motion where the acceleration is constant. It's just that we know in the air with projectile motion that vertical acceleration is constant. So it's an example of that. So what they've done in the H's, V's, and A's is plug in the appropriate known points so that you can use them for projectile motion. So H is easy because acceleration is 0. We get that in the horizontal direction, it just keeps going at a constant speed, assuming there's no there is no wind resistance. It just keeps going at a constant speed. And if you take equations 1, 2, and 3 and make A equal to 0 in each one of them, so V2 equals V1, which means the velocity at time 2 equals the velocity at time 1, whatever time 1 and time 2 are. The distance equals the velocity times time, because that whole last part would fall out, which is what 2h is. And the last one, again, if A was 0, it would be V2 squared equals V1 squared. So again, it's the same one as saying V2 equals V1, which is just a given. So the only one you're left with is 2 for the horizontal. For vertical, it describes 2 scenarios. One is where you're going from the apex down to landing, and those are your V's. So if I dropped a ball right here, where I started at the apex and then I went to the ground, my velocity at time 0, which is 0, in my vertical velocity, these are just, we're only looking at vertical right now. My vertical velocity at time 0, meaning just when I let it go, is 0. It then speeds up and speeds up and speeds up until it lands. But at time 1, we know that it's 0, and time 2 is when it lands. So in all of these 3 equations, they have a velocity 2. If you plugged a V1 equals 0 into 1, 2, and 3, you would see that you will get equations 1v, 2v, and 3v. Now, in all of these cases, your acceleration, technically in all of these cases, you're putting in an acceleration of minus 9.81, which means your velocity, let's say in 1v, is going to equal a negative velocity, because we know that, if the acceleration is negative and it starts at 0, it's going to keep, the velocity is going to keep increasing in the negative direction. That's the definition of a negative acceleration. So we're just, and that makes sense. And the same with the distance. It's the distance from the top down to the bottom. For the last two, the 1A and the 2A's, this is, let's say we are starting from the beginning and we're going to look at the time up to the apex. So we start with a positive velocity and then we keep getting slower and slower and slower and slower and slower until we hit the top, which is our time period 2. So often for those vertical ones, this is time period 1 and this is time period 2 for the 1A and 2A equations. Those equations. For the 1V, 2V, and 3, this is time period 1, and this is time period 2 for the other 3. Does that help?
Yes, that helps. That helps to put it more into more context. Thank you.
Okay, I think there was somebody else who had a question in there.
Oh, it was me. I just wanted to ask, what would happen if the projection height wasn't 0?
Oh, that's a very good question. It's one it's an important question. It's a very important question. I will let you know that I won't, because most of the questions you're given are projection height equals 0, so we won't do it. What happens with projection height equal to 0 or not equal to 0 is we have to look at what happens in the first half or first part from takeoff up to the apex, and then what happens from the apex down as two separate things. So we would find the time to the apex. So let's say I know that it takes off at 10 meters per second at 35 degrees, which means the vertical velocity at time 1 is, sorry folks, 5.73 meters per second. And if you just hold on, I'm just going to close the door for a second. Sorry, somebody came to the door. Usually he's very, very quiet. I hardly know he's here, but always during a class. Okay, so we know that we would have a vertical velocity of 5.73 at takeoff here. We know we would have a vertical velocity at here at the apex of 0, and we know that that would take us 0.58 seconds to do. If then we would start again and we would say we have, oh, and we would figure out how far up that was. We would figure out that that was 1.68 meters. Let's say we know that this person was only got it just on the ground. So down here, and it went another meter down. So he managed to catch it just before the ground and it was another meter. So the distance down would actually be 2.68 meters. And once you knew that, you could use equation 2V to figure out the time to get down. So that's what we would do if they weren't symmetrical like this. If it took longer coming down, or if it took shorter, it could have been that they reached up really high and it didn't come down as far before they got it. But it would mean that it would be 0.58, the time in the air that we would use in here for how far it would go would be 0.58 seconds going up, and then probably something more in the order of 0.65 seconds coming down because it took longer to come down. Does that make sense?
Yeah, would we have a question like that on the midterm?
No,
Okay.
that's what I prefaced that with, is that
Yeah.
it's important to know, and there are many problems that are like that. I wouldn't make you do the math of that. I would expect you to know something of the nature of the graphs where we talked, like figure 1015, where you have some sense that of what happens in those cases where the projection height is not 0, because figure 1015, you know, shows you that what happens there. It shows you, you know, what would be, which one would have the largest range, so horizontal distance range, depending on whether you have a positive or a negative projection height. So whether you're less than 45 or greater than 45 degrees would take you farther. And the idea that if you looked at that figure, you could actually see that, you know, it's shorter on the way down on the bottom one, and it's longer on the way down in the middle one. You know, those kinds of questions, that's more of a theory question, but to do the actual math of it, no.
Okay. Yeah, thank you.
Any other questions on this one? Okay. Just confirming, somebody wanted chapter 11, introductory problem 8. Still? Okay. It's very simply measuring angles at the, I think I did it in the lecture. So where you figure out where the angle is. If it's a relative angle at a joint, it's between the two segments. So between, you put your protractor on the trunk and you measure the angle between that and the upper arm to get your shoulder, between the upper arm and forearm to get your elbow. And then the absolute angle, you have to define whether you're going to do it with respect to a particular, like a right horizontal, for example. You would draw the right horizontal at your bottom of your upper arm, and then measure from that up to your upper arm. Any other questions?
Professor, I don't know if you did chapter 11, additional problem number 10. Did we do that one already?
We haven't done it today. We
Okay.
can do that. So chapter 11, additional problem 10?
Yes, please.
Happy to. Okay. So a speed skater increases her speed from 10 meters per second to 12.5 meters per second over a period of 3 seconds while coming out of a curve of 20-meter radius. What are, the magnitudes of her radial, tangential, and total accelerations as she leaves the curve. This is a classic radial tangential acceleration question. So they are coming up the straightaway, and then they go into a curve, and then they go into the straightaway again. And that curve has a radius of 20 meters. And the velocity at time 1, so let's say this is time 1. And time 2 occurs right here. Right when they're coming out of the end of the curve, and they're going to just keep going straight, and this would be a tangent, right? If you're just coming out straight, that's tangential to the thing. So V1, so velocity at time 1 equals 10 meters per second. Velocity at time 2 equals 12.5 meters per second. T2 minus T1 equals 3 seconds. So that's the T involved there. So what are the magnitudes of a radial, tangential, and total accelerations as they leave a curve? So they leave the curve is time 2. Assuming a constant increase in speed between T1 and T2, we can assume that this is going to be a constant acceleration, and that is the tangential acceleration, because the tangential acceleration reflects the change in speed. Because your velocity at any instant in time is always going to be tangential to, so that's V1, tangential to the point. And what does tangent mean? Well, if you draw your radius and you draw your velocity, this is actually a 90-degree angle. It's the instantaneous slope of the curve. And this is going to be velocity 2. So the change in speed, the magnitude of your velocity is going to be this is meters per second, and this is seconds, so that's going to equal
0.83 meters per second.
Okay, so that's the change in magnitude of the speed. But even if you were going around a circle, if this speed skater was going around the curve at a constant speed, they would still have a radial acceleration at each point in time, because the radial acceleration is the acceleration associated, and it's pointed towards the center of the circle. And that is the acceleration required to change direction. Because think about it, you've got acceleration is a change in velocity over a change in time. And velocity is a vector and has both a magnitude and a direction. So as you're going around a curve, the direction is changing. The magnitude may or may not be changing. In this particular case, it is changing. But the direction is also changing. And because there's a change in direction, there's an acceleration just associated with that change in direction. So AR equals V squared over R. Now, this is instantaneous. The radial acceleration has to do with what the current velocity is and the current radius is. Because the magnitude of this velocity is actually changing, the radial acceleration is actually going to be changing throughout this curve. But they ask for it right here at time 2. It says, what is the radial acceleration as you're coming out of the curve? So it's just before you exit the curve. And so that's going to be V2, which is 12.5 second squared, divided by our radius, which is 20 meters. And this will be second squared. This will be meter squared. That will cancel this squared there. So we'll be left with meters per second squared. So 12.5 squared divided by 20.
7.81.
So there's 2 components of acceleration on the person as they come out. So as they're coming out of this curve, they have a tangential acceleration of 0.83 meters per second squared, and they have at 90 degrees to that, a radial acceleration of 7.81 meters per second squared. And actually, let's just make this guy smaller because obviously he's a lot smaller than that. So if you add those 2 together, I'm going to start at the bottom of N, end at the tip of the other. So that is your total right there. That's your total acceleration because you've got 2 components that are 90 degrees from each other. You can now, you combine them using Pythagorean. So A is going to 7 square root of 7.81 meters per second squared plus 0.83 meters per second squared. And the square root of it is
7.86.
And again, there could be round off in there. So, any questions on that? Any questions? Straightforward? Okay.
So for radial accelerations, the smaller the radius is, the harder to change direction. So the high is radial acceleration, right?
Yeah, so the radial acceleration, the higher it is, the harder it is to change direction. So think about on a snowy, icy day, and you're going around a curve. The faster you go, the harder it is to make the curve, right?
Yes.
Yes.
And
So
the smaller the radius.
And the
so
smaller the
it's,
radius, the tighter the curve is, the harder it is to make the curve. So if you're going fast,
So we need,
so go ahead. Sorry, go
we
ahead.
need more force to change the direction, right?
Yes. Yes. We haven't got to there, but yes, that's absolutely correct. Yeah. And you
Thank you.
feel it. Okay. So any other questions on this question? Okay, I think Danny, you have your hand up.
Yes. Professor, I was wondering if we could do number 8. same chapter 11 additional problems.
Okay, the cyclist.
Yes.
The curve. Okay.
Thank you.
Okay. A cyclist enters, so this is chapter 11, maybe. Cyclist enters a curve of 30 meters radius at a speed of 12 meters per second. As the brakes are applied, speed is decreased at a constant rate of 0.5 meters per second squared. What are the magnitudes of the cyclist's radial and tangential accelerations when his speed hits 10 meters per second? So again, we're coming into a curve. That's a really bad curve. And they come into the curve at a speed of 12 meters per second. The curve has a radius of 30 meters. They put the brake and the speed is decreased at a constant rate of 0.5 meters per second. Well, they basically are telling you what your tangential acceleration is. The tangential acceleration, which is the change in the speed, is negative 0.5 meters per second squared. Negative because it's decreasing the speed. And that's the definition of the tangential acceleration. So this is time 1. And at some point in here, time 2. The speed is going to decrease to the point where it's 10 meters per second. So that's time 2. We have, what we want to know is, what is their radial acceleration at this point in time? Radial and tangential acceleration. So we're looking for AR. So we're basically looking at AR at time 2. We know that the tangential acceleration is constant throughout the curve, and it's minus 0.5. So even at time 1 and at time 2, time 1 being when they enter the curve at 12 meters per second, time 2 being at the point where their speed has decreased to 10 meters per second. Both of those, the tangential acceleration is going to be negative 0.5 meters per second. And the radial at time 2, when it's 10 meters per second, is going to be 10 meters per second all squared, divided by the radius, which is 30 meters. So we've got 100 meters squared per second squared. And so one of the meters will cancel and we'll be left with meters per second squared. And 100 divided by 30, which is 3.33. Any questions on that one? Here. Okay.
Professor?
Yeah.
Sorry, I was just wondering, will you be having office hours tomorrow since you're not going to have on Thursday, or?
I have them on Thursday. Unfortunately, the past after the midterm, not kind of useless. I have to let you know on that. I have a meeting tomorrow. I probably can have some tomorrow. I will post if that happens.
Thank you.
You're welcome. Any other questions? All good? No. Can't tell you the breakdown of marks per sec per. Any other questions? All good? Okay, I'm going to stop the recording then.